Hey everyone, Isaac here. In today's video, we're going to talk about measuring quantum circuits in PennyLane. Now, it's fair to say for most programming languages and software packages that are out there, this topic does not deserve its own video. When you're debugging and prototyping your own code, you can print out variables at any point that you want. And doing this sort of readout doesn't change anything about the computation that you're doing, it just maybe slows it down a little bit. But when it comes to quantum computing, things are a little bit different. Reading out information from a quantum system, i.e. doing a measurement, generally causes its state to change and can therefore destroy the computation you're trying to do. All this means is that when you're using real quantum hardware, you can't be doing readouts and measurements willy-nilly. This means that we'll usually be debugging and prototyping our code on a simulator rather than real hardware. So why does a simulator give us more flexibility here? Doing a full simulation of a quantum computation requires computing the states of every qubit at each point in the circuit. We can use that to predict what a measurement would give us at any point, and we can even read out the full quantum state to compare what our simulated circuit does versus what we actually expect it to do. The standard simulator device in PennyLane is called Default Qubit, and for more information on all the other devices that are in PennyLane, see our video linked in the description below. Next, we'll look at what measurements we can do with simulators, and then we'll check out what changes when we instead want to use real hardware. Let's get coding. Okay, here we are in a notebook on the Xanadu Cloud platform. If you're unfamiliar about Xanadu Cloud and how to make an account and access PennyLane, all of our other software packages, and some of our hardware for free, make sure to check out a video linked in the description below for that. As always, we're going to import PennyLane as QML, and we're going to import PennyLane's wrap version of NumPy 2. The next thing we need to do is actually make a quantum circuit so that we can perform measurements on it. Make sure to check out our video on how to create quantum circuits in PennyLane linked in the description down below. We need a device to run our circuit on, so let's just use the default qubit simulator as I alluded to before. And let's say our quantum circuit has 2 qubits in it. And for our circuit, we're just going to create the following 2-qubit circuit that you see on the screen right now that contains a Hadamard gate and a CNOT gate. Let's call our circuit, and it's going to take no arguments. And then again, it just has a Hadamard and a CNOT gate in the circuit, and that's it. For now, we're going to say that our quantum function returns QML.state. We'll talk about this a little bit more because that's the actual measurement being done. And finally, we just have to decorate our circuit with @QML.QNode and give it the device. Now, as I alluded to before, we might want to use a simulator to check that the full quantum state that our circuit produces is actually what we expect it to be from a theoretical perspective. Now, if you're familiar with Bell states and the Bell basis, this circuit actually creates the following Bell state on the screen. And we have the luxury of being able to check whether or not our circuit's actually creating this state because we're running it on a simulator device. So calling the circuit above, we can indeed see that the state it produces is the Bell state as intended. Now, what if your state was, say, best described by a density matrix instead of a state vector? Well, instead of calling QML.state, we can call QML.density matrix. And the density matrix method just requires that we supply it the wires that we would like to know the state of. You can supply the entire system. So in this case, it would be wires equals range of 2. And in this case, what it gives is the outer product between the ket state vector and the bra state vector, which gives us a 4x4 matrix in this case. Now, you don't have to give density matrix the entire system of qubits. You can supply a subsystem of qubits. So let's just say we wanted to know the density matrix representation of the state associated to the first qubit. Now here, the resulting density matrix is a 2x2 matrix, which is what we should expect for a density matrix corresponding to 1 qubit. And this is obtained by partially tracing out the other qubit that's not involved in the system of interest. In this case, it's the second qubit. The next measurement we'll look at is QML.probs. QML.probs will output the probability associated to measuring each computational basis state. These probabilities are calculated using the Born rule, which is a fundamental postulate of quantum mechanics. Now, what we need to pass QML.probs is a list of wires. And in this case, let's just pass it all of our wires in our system, and let's see what this gives us. So here, what our circuit outputs is essentially an array containing the probabilities of measuring the 0,0 state, the 0,1 state, the 1,0 state, and the 1,1 state. And as expected for our Bell state, the only non-zero probabilities are the ones associated with measuring 0,0 and 1,1. We can also ask QML.probs to give us a marginal probability by giving it a subsystem of wires involved in our system. So let's say we only give it the first qubit. Let's see what that gives us. Now, as I said, this is a marginal distribution where the entries in this probability vector are the associated probabilities of measuring qubit number 1 in the 0 state or in the 1 state. In this case, both probabilities are 50%. And if we instead maybe try this out for the second qubit, we actually get the same result in this case. This is a property of the Bell state. So to summarize so far, we've looked at 3 different measurements. We've looked at QML.state, which gives us the full vector representation of our quantum state in the computational basis. We looked at QML.density matrix, which gives us the density matrix representation of our quantum state, and QML.probs, which given a set of wires, gives us the probability of measuring each computational basis state. But let's now talk about what changes when we want to measure things from real quantum hardware. With real devices, we have to sample or query them, where the number of queries or samples defines the number of times we need to evaluate our circuit in order to estimate the desired quantity that we want to measure. To take this into account in PennyLane, when defining a device, we can specify the number of times, which we call shots, that we want to evaluate the circuit to estimate the quantity we want to measure. In our example that we just looked at, we didn't specify shots at all, indicating that we were just going to carry on with our computation, knowing full well what the quantum state of every qubit was at every point in the computation. So when we define a device in PennyLane and specify a finite value for shots, we're ruling out the ability for our quantum circuit to read out QML.state, QML.density matrix, and any other measurement that involves full knowledge of the quantum state at every step in the computation. So let's specify a finite shot device with the circuit we just created and look at some measurement outcomes that are tailored towards finite shots and real quantum hardware. Okay, we're back in our notebook here, and all we're going to do is specify a shots keyword argument within this device definition. So we're going to say shots equals, let's say 5, which means we're going to evaluate our circuit 5 times to calculate some measurement outcome for real quantum hardware. And just a quick side note, yes, we are still using the default qubit simulator, but by specifying a finite value of shots within the device definition here, we are truly simulating real hardware. In fact, if I try and return QML.state from this circuit running on a device with finite shots, I'll get a warning from PennyLane. And the warning actually makes a lot of sense. It says, I requested state or density matrix with finite shots, and the returned state information is analytic and unaffected by sampling. All this is trying to say is that if instead we were using an actual piece of hardware rather than a simulator simulating real hardware, this would not work. So now let's look at some measurements that are designed to work on real hardware and won't give us any warnings like this one. The first measurement outcome we'll discuss is QML.sample. QML.sample will simply return raw basis state samples that are theoretically sampled according to the probability distribution defined by the underlying quantum state of our circuit. Now, this doesn't mean that we're accessing the full quantum state in the computational basis. It means we're simply measuring the quantum state in the computational basis. So for our Bell state that we prepared, the possible basis states that I could sample are 0, 0 and 1, 1 with equal probability. When we call QML.sample, these should be the only outcomes that we see. And indeed, that's what we see when we run our circuit. Each row in this array that QML.sample produces is one shot, and the row is the actual measurement outcome. So in the first shot, we sampled the 0, 0 state, then the 1, 1 state, the 0, 0 state, and so on. There's another measurement that we can do that's really similar to QML.sample, but it's a bit more compact, and it's called QML.counts. QML.counts compactly shows the outcomes of sampling a circuit, but as a dictionary containing the possible measurement outcomes and the number of times the measurement outcome occurred. So running this circuit with QML.counts instead of QML.sample, we see a dictionary whose keys are 0, 0 and 1, 1, the possible measurement outcomes, and the values are the number of times the measurement outcome occurs. So we measured 0, 0 3 times, and we measured 1, 1 2 times. Now, if you recall QML.probs, it was giving us the probability of measuring each computational basis state. With a finite shot device, we can actually approximate what that probability distribution is of measuring each computational basis state by way of sampling the circuit many times in the computational basis. Essentially what's happening under the hood is instead of using the Born rule to calculate probabilities exactly, we're instead using a frequency distribution. Having QML.counts here is actually a really good way of visualizing how we can approximate the probability of measuring each computational basis state with a finite shot device. If I were to approximate the probability distribution right now with these samples in the computational basis, I would say that the probability of measuring 0, 0 based on my 5 shots is 3 over 5 or 60%. And same for 1, 1, it would be 2 over 5, which is 40%. And if I increase the number of shots to say like 100, I would expect that this approximation, this frequency distribution approximation of my probability distribution of measuring each computational basis state would get closer and closer to what I expect theoretically, which is 50-50, 0, 0, 1, 1. And as you can see, this is a little closer to the exact result. Now let's just actually show this using QML.probs. So here, with using 100 samples in the computational basis state and using a frequency distribution to approximate my probability distribution, I'm getting that the probability of measuring 0, 0 is about 55%, and the probability of measuring 1, 1 is 45%. And again, this gets more and more accurate as I increase the number of shots. Let's try like 1,000. And as you can see, we're getting closer and closer to 50% in 0, 0, 50% in 1, 1, which is what we'd expect theoretically. Okay, now what about expectation values? To measure expectation values in PennyLane, we need to return qml.expval. Then we just need to supply it the operator that we want to measure the expectation value of. And in this case, let's just use the example of the polyz operator on the first qubit. Now, if I get rid of this shots argument in the device definition up here, this implies that we have full knowledge of the quantum state of every qubit at every point in the computation, meaning that at the end of the day, when we measure the expectation value of the polyz operator, we'll get exact measurement statistics that exactly match what we would expect theoretically. And running our circuit here, we get a value of 0, which is what we expect. But putting back in this finite shots value, we will not be getting exact measurement statistics, meaning that my expectation value here will be slightly off from what we expect theoretically. In this case, I got a value of 0.2, and if I run this again, it'll be slightly different. And to kind of illustrate what's going on here a bit more in detail, we can again go back to qml.sample. Now, qml.sample can take no arguments, but it can also take an operator as an argument, and let's see what happens when we do that. When we measure an observable experimentally, we expect the outcomes to be eigenvalues of the observable. And in this case, our observable, the polyz operator, has eigenvalues -1 and +1. Now, when we look at the average of all of these results, this is what qml.expval is giving us when we use a finite shot device. So as I said before, we're not getting exact measurement statistics here. So let's say we want to evaluate our circuit with 5 shots, 50 shots, 100 shots, 500, and 1,000 shots. Let's see what the measurement statistics look like. So the result here, when you specify many different shot values, are going to be an array where each entry corresponds to the shot amount you specified. So the first entry corresponds to 5 shots, the next one corresponds to 50, 100, 500, 1,000. And as you can see, as we increase the number of shots, we're getting a better estimate at the actual expectation value had we had access to the actual quantum state at every point in the computation. Whew, that's a lot of different measurements we can return from QNodes. Measurements are extremely important in quantum machine learning, quantum computing, and in quantum chemistry, as they're the key for us to be able to see what our quantum algorithm should be doing, where we can use a simulator to verify some results we expect, or what our quantum algorithm actually is doing, where we've actually implemented it on real hardware and we need to use measurements to check some outcomes. Given that, it's important to understand measurements in the context of simulators versus real hardware. And to summarize, on simulators, we can return quantities with exact measurement statistics or things that involve the full quantum state of our circuit, whereas with real hardware, we don't have that luxury. We're only able to return quantities with inexact measurement statistics based on how many times we evaluated the circuit, which we called shots. Now, there are quite a few other measurements that we didn't talk about today that are also available in PennyLane. Make sure to check all those measurements out and all of their intricacies with the link in the description down below. If you have any questions, please leave a comment down below, or you can join our public Slack channel or our discussion forum, and the links for those are in the description as well. If you enjoyed this video, make sure to share it around with your friends, give us a like, and subscribe for more quantum programming content from Xanadu.